Somebody once taught you a lie about the universe, and they taught it to you with a balloon. You've seen it. Maybe a teacher did it at the front of a class. Maybe it was a science show on a screen. They take an ordinary party balloon and they ink a few little dots on it with a marker. Those are the galaxies. And then they blow it up. And as the rubber swells, every dot drifts away from every other dot. The ones nearby ooze apart slowly. The ones far across the curve race apart fast. And the teacher smiles and says, "There." That's the universe. Everything rushing away from everything else in every direction. That's what expansion looks like. And it's a lovely demonstration. It's clean, it's true to the data. And I am about to take a hammer to it because that balloon is a fraud. Here's the swindle. Watch what the balloon actually does when you blow it up. It gets bigger by pushing into the room. It shoves the air in front of it out of the way. A second ago, that particular cubic inch of your kitchen was full of air, and now it's full of rubber because the balloon expanded into a space that was already sitting there waiting for it. The balloon grew by claiming territory, by moving into the outside. So let me ask you the only question that matters, the one the demonstration quietly skips. When the universe expands, what is it moving into? What's the room? What's the air it shoves aside? Is there a cosmic living room out past the last galaxy? Some black warehouse that the universe is slowly filling up? Is it God's back garden? An endless wasteland of nothing? With a frontier somewhere? An edge where the stuff stops and the empty begins? And be honest, the second you actually tried to picture that, something in your head snapped taut, like a knot pulling tight. Because there's no good answer. Out past everything, there's more stuff? Then that's part of the universe too, and you've just moved the question. There's nothing out there? Then what's the universe expanding into if out there doesn't exist? Every road dead ends. The harder you push on it, the more it feels like the question is broken. It is. And I want to tell you right now, before we go one step further, that knot in your head is not your fault. You are not failing to understand this. You are running at full speed into the one thing your brain was physically built never to be able to picture. Let me show you what I mean, because it's stranger and kinder than it sounds. For a few 100 million years, the animal that became you survived by answering one question, over and over, faster than anything else. Where's the edge? Where's the line between the grass and the clearing? Because that's where the lion waits. Where's the mouth of the cave? Because that's the difference between shelter and exposure. Where does the safe thing stop and the dangerous thing begin? An animal that's good at finding edges eats dinner. An animal that's bad at it is dinner. So your brain got very, very good at finding edges. So good that in 2008, a team of neuroscientists, Edward and Maybrit Moser and their colleagues, building on a prediction John O'Keefe and Neil Burgess had made back in 1996, went looking inside the mammalian brain and found actual cells whose entire job is this. They're called border cells. They sit in a strip of tissue called the entorhinal cortex, and they do basically nothing all day until the animal comes near a wall or a boundary or an edge, and then they fire. You have, sitting in your skull right now, a dedicated piece of biological hardware that lights up at edges. The developmental psychologists Elizabeth Spelke and Catherine Kinsler have shown that even babies in their first months carve the whole visual world up into separate, bounded objects before they can do almost anything else. Everything has an edge, and past the edge is an outside. Isn't an opinion you hold. It's closer to an organ you grew. So when the universe turns out to have no edge and no outside, The vertigo you feel is not stupidity. It's an exquisitely well-built sense organ, firing into a room with no walls, looking for a line that was never there. Which means the famous question, what is the universe expanding into, is a perfectly grammatical sentence with a typo buried in it. It's the cosmic version of asking, what's north of the North Pole? Nothing's wrong with the grammar. North is a real direction. The North Pole is a real place, and the sentence sounds completely sensible right up until you're standing at the pole itself, turning in a circle, realizing every direction you can point is south. The question wasn't hard. It was malformed. And the whole job here is to find the typo in expanding into, to take a hammer to one box after another that your edge-finding brain keeps building, knock the walls out, and learn to picture a universe that grows without ever, anywhere, having an outside. I'll warn you, this gets a little like motion sickness in places. There's a part near the end I genuinely lose sleep over. But there's something waiting behind the very last wall. Something about you, specifically, the ordinary you sitting wherever you're sitting. And I'm not gonna tell you what it is yet. We have walls to knock down first. One quick thing before we pick up the hammer. If you'd like more nights built like this one, the subscribe button is down there somewhere. Think of it as the one box in this whole episode with a door. So let's go knock the first wall out. To do that, we have to rewind 114 years to a freezing dome in the high desert of Arizona, where the loneliest man in the history of astronomy is about to catch the entire cosmos in the act of running away. The year is 1912. The place is the Lowell Observatory, perched up in Flagstaff, Arizona, and the man inside is named Vesto Slipher. And if there were a contest for the most underrated person in the story of the universe, Slipher would be a finalist who never even got told he was nominated. Here's his problem. Out in the sky, there are these faint smudges astronomers call spiral nebulae, little pinwheels of dim light. Nobody knows what they are. Most people figure they're clouds of glowing gas, smears on the lens of the cosmos. Slipher wants to know how fast they're moving, and to do that, he needs their spectrum. He needs to spread their light out into a rainbow and read the dark lines in it, the way you'd read a barcode. The trouble is, these things are pathetically faint. Catching enough of their light to read takes him a single exposure lasting 6 hours in a cold dome, hand-guiding the telescope, then reading the result off a photographic plate with a hand-cranked micrometer. And here's the detail I love, the one that should make every gadget lover's heart ache a little. The reason Slipher could pull this off at all is that in late 1912, he bolted a commercial portrait lens onto the front of his spectrograph, a Voigtlander, the kind of fast glass a photographer would use to shoot a wedding. Off-the-shelf camera glass, the sort of thing you could buy. That's the instrument that first caught the cosmos fleeing, a wedding lens, in a freezing shed in Arizona. And in September of 1912, he points it at the biggest, brightest of these smudges, the one in the constellation Andromeda, and he reads the barcode. And the lines are in the wrong place. Every dark line that should sit at a particular spot has been shoved bodily toward the blue end of the spectrum. Now, here's the trick of it, and it's a trick you already know with your ears. You've stood on a sidewalk while an ambulance screamed past, and you've heard the pitch of the siren drop the instant it goes by, high and tight as it comes at you, low and slack as it pulls away. That's because the sound waves get squashed together when the thing is approaching and stretched out longer when it's receding. Light does the exact same thing. Squashed up light shifts toward blue. Stretched out light shifts toward red. Slipher's Andromeda is shifted blue, which means it's coming at us. And when he does the arithmetic, it's coming at about 300 kilometers a second. Faster than any object anyone had ever clocked. He keeps going. He grinds out spectrum after spectrum, year after year, mostly alone, mostly ignored. And by 1917, he's got 24 of these spiral smudges measured, and almost all the others are shifted the other way. Redshifted, stretched, fleeing. Of 41 he eventually hands the astronomer Arthur Eddington, only 4 are coming toward us. The rest are all running away at hundreds of kilometers a second. The evidence that the universe is on the move was sitting in Vesto Slipher's notebooks a full decade before the world noticed. He just didn't have the one other piece you needed to know what it meant. That piece came from a bigger telescope and a much better publicized man, Edwin Hubble, up on Mount Wilson in California with the most powerful instrument on Earth. Hubble does 2 things. First, he proves those smudges aren't gas clouds inside our own galaxy at all. They're other galaxies, whole separate islands of 100 billion stars each, unthinkably far away. And second, this is the one that should give you a chill. He lines up Slipher's speeds against the distances, and he finds a law. The law is this: the farther away a galaxy is, the faster it's running away from us. And not vaguely, proportionally. Double the distance, double the speed. It's as if you walked into a party and the moment you arrived, everyone bolted. But in this strange, orderly way, where the person standing 1 meter from you backs off at a gentle stroll, and the person 10 meters away sprints for the door 10 times faster, and the person 100 meters off is gone like a shot. That's not a panic. A panic is chaos. This is organized. This is the whole room obeying one clean rule about how fast to flee, keyed exactly to how far away you already were. And right here, right at the moment the universe is revealed to be flying apart in this lawful, premeditated way, almost everyone, including some very smart physicists, builds the first box. The wrong box. It's so natural, you've probably already built it yourself in the last 30 seconds. The box is this: an explosion. Picture a grenade sitting in the dead center of an enormous, empty, black warehouse. It detonates. Shrapnel sprays outward in all directions, fast bits flying farther than slow bits, all of it tearing out into the empty space of the warehouse that was already there. And isn't that exactly the picture? The Big Bang was the grenade, everything's the shrapnel, space is the warehouse, and we're all just hurtling outward through it. Take that picture and throw it in the bin. I don't mean adjust it. I don't mean it's a little oversimplified. I mean it is catastrophically wrong. Wrong in a way that will quietly poison everything else if you let it stay. Because look at what the warehouse smuggles in. It smuggles in a center, the spot where the grenade sat. It smuggles in a frontier, the leading edge of the fastest shrapnel. And it smuggles in an outside, all that empty warehouse the shrapnel hasn't reached yet. A center, an edge, and an outside. Your border cells love this picture. It is built entirely out of the thing they're hungry for. And every single one of those features is a fiction. So to get the right picture, we have to put down the grenade and walk out of the armory and go into the kitchen. Because the truest homely image anyone ever found for this isn't a weapon. It's a loaf of bread. Picture a lump of raisin bread dough, raw, studded with raisins, sitting on the counter. The raisins are the galaxies. The dough is space itself. Now, slide it in the oven and watch. The dough rises. And as it rises, every raisin drifts away from every other raisin. But here's the thing, and this is the whole secret of the universe, so I want you to really hold it. The raisins don't move. They don't crawl through the dough. They don't sprout little legs and swim toward the crust. Each raisin sits perfectly still in its own patch of dough. What's happening is that new dough is appearing between them. The dough in the gap puffs up and makes more of itself, and that fresh dough carries the raisins apart, not because they're traveling, but because there's simply more between them than there was a minute ago. And now, Hubble's law just falls out of the oven for free. Take two raisins close together. There's only a little dough between them, so as it rises, they drift apart slowly. Take two raisins far apart. There's a lot of dough between them, all of it rising at once, so they fly apart fast. Farther apart means more rising dough in the gap, means faster recession. The orderly party, the proportional flight, it's not the raisins fleeing. It's the between multiplying. The universe isn't an explosion of things hurtling through space. It's a quiet, everywhere at once swelling of the space itself. And the moment you've got that, the second box cracks open all by itself. The box that says there has to be a center. Go and sit on the raisin in the very middle of the loaf. From there, you look around, and every other raisin is fleeing away from you, the far ones faster than the near ones. Obviously, you're at the center. Of course, everything runs from you. But now, hop over and sit on a raisin way out near the crust. Look around from there, and every other raisin is fleeing away from you too. The far ones faster than the near ones. The exact same view. Hop to the most forsaken corner raisin in the whole loaf, the runt jammed against the pan, and look around. Everyone is fleeing you in perfect Hubble order. There's no special reason. Every raisin sees itself as the still point at the heart of a universal stampede, because every raisin has dough swelling on all sides of it. And so the thing that sounded like cosmic homelessness, there's no center, turns out to be hiding a second sentence inside it, one we are going to come back to at the very end. So tuck it somewhere safe. There's no center, which is the same thing as saying every point is the center, including, by the way, the spot you're sitting in right now. And when people ask, where did the Big Bang happen? The honest, vertiginous answer is everywhere. It happened on the tip of your nose. It happened in your teacup. It happened in the dead center of the Andromeda Galaxy, and in the patch of floor under your feet, all at the same instant. Because it wasn't a bang at a place. It was a stretching that started in all of space at once. And do you want to know who was the first human being to truly get this? To look at the math and see that space itself was growing? It wasn't Hubble. It wasn't Einstein. It was a Belgian priest. His name was Georges Lemaitre, and in 1927, 2 years before Hubble published his famous law, Lemaitre sat down with Einstein's own equations of gravity and worked out, in his spare time, that the universe must be expanding. He even estimated how fast. He published it. And because he published it in an obscure French-language Belgian journal that almost nobody read, the discovery just sat there, ignored, while history got ready to hand the credit to someone else. Lemaitre knew he was on to something, though, and that same year, he got his chance to tell the great man himself at a grand physics conference in Brussels. He worked up the nerve and explained his expanding universe to Albert Einstein. And, by Lemaitre's own account, recalled years later, so take the exact wording as one man's memory of a sharp afternoon, Einstein listened and then delivered one of the most beautifully cruel reviews in the history of science. He told the priest, "Your calculations are correct, but your physics is abominable." Which, if you translate it out of politeness, means roughly, your math is flawless, and your understanding of reality is garbage. It's the cosmic equivalent of the greatest basketball player alive watching your jump shot and saying, "Lovely form. You will never, ever play this game." The priest was right. The genius was wrong. Einstein was so wedded to the idea of a serene, eternal, unchanging cosmos that he couldn't stomach a universe that grows. And we'll get to just how badly that stubbornness bit him later, because it produced what the story says he called the single biggest blunder of his life. For now, the priest has handed us the next question, and it's a hard one. If the dough is what's growing, if space itself is swelling, then what on earth is space made of? What is the stuff that can do that? To answer that, I have to knock down a box you've been carrying around your entire life without noticing. A box built by Isaac Newton. For Newton, space was simple. Space was a stage. It was a vast, rigid, empty container that the universe got placed into. Fixed, absolute, indifferent. Think of your grandmother's old biscuit tin, the one with the faded flowers on the lid. Take all the biscuits out. What's left? The tin. Empty. Unchanged. Exactly the same shape it always was, just with nothing in it. That was Newton's space. The tin that's still there after you remove every star and galaxy and atom. Empty space was just nothing. A passive box, and it could no more stretch or grow than the dimensions of an empty room could. And for 200 years, that was the picture. Until a sockless genius in Switzerland picked up the biscuit tin and smashed it on the floor. Einstein's space is not a tin. Einstein's space is toffee. I mean that almost literally. Picture an enormous, invisible, slightly springy slab of toffee filling everything. And that slab is what space is. It's not an empty container that things sit in. It's a physical thing in its own right. It can bend. It can stretch. It can ripple and vibrate. And this is the part that rewired physics. It bends under weight. Put a heavy ball on the toffee, and the toffee dents around it. That dent is gravity. The Earth doesn't reach out with some invisible rope and pull the moon. The Earth just dents the toffee around it, and the moon rolls along the curve of the dent, like a marble circling the inside of a bowl. There's no pulling. There's just shape. A fish, they say, can't see the water it swims in, but the water is absolutely there, and the currents in it decide which way the fish gets to go. That's us, in the toffee. We can't see space, but it's a real, physical substance, and the moment you understand that space is a thing rather than an empty stage, the impossible suddenly becomes ordinary. Of course it can grow. It's made of something. A tin can't stretch. Toffee can. But the toffee, lovely as it is, still leaves the bread analogy with a crack in it that I have to fix, because that crack is exactly where people's understanding breaks. When bread rises, the dough puffs up because yeast gas is filling in from inside the dough. Stuff gets added. And that quietly plants a wrong idea that the universe expands because some cosmic stuff is being poured into the gaps. It isn't. Nothing is being poured in. So I'm going to retire the bread now, thank it for its service, and put it away, and hand you the cleanest picture anyone has ever found for this. It's the one you're probably holding in your hand right now. It's your phone. Picture two bright stars on your phone screen, sitting 10 pixels apart. Now, I don't want you to make the screen bigger. The screen stays exactly the same size. Instead, I want you to raise the resolution. Slip a brand new pixel in between every existing pair of pixels. Where there were 10 pixels of gap, now there are 20, 40, 80. What happened to the two stars? Absolutely nothing. Neither star moved. Each one is sitting on the exact same spot it always sat on. Its pixel address never changed. And yet the distance between them, measured in pixels, has quietly quadrupled. The stars held still. The ruler grew. New space appeared between them, not poured in from somewhere, just minted right there in the gap, out of nothing, everywhere at once. That right there is the real, true, grown-up face of the scary phrase you've heard physicists use, metric expansion. Metric just means measurement, the ruler. Metric expansion means the ruler itself is getting longer, everywhere, all the time. Not that the galaxies are racing across some fixed grid, but that the grid itself is swelling underneath them while they sit perfectly still. And here's the one place the universe is even cleaner than your phone. A phone screen has a maximum resolution, a finest possible pixel, little visible squares if you squint. Space doesn't. There's no smallest pixel, no grain, no seam. It's smooth, gapless, infinitely divisible jelly that can keep inserting more between forever and never, ever tear. And the instant I say that, somebody puts up a hand. I can hear it. Hang on, wait. If space is constantly stuffing new pixels in between everything, then why doesn't it stuff new pixels between the atoms in my arm? Why isn't my arm getting longer right now? Why hasn't the Earth gone drifting away from the sun? Why is anything still holding together? It's the best question, and the answer is wonderful. The reason is that this expansion, this minting of new space, is staggeringly, pathetically weak. It's the gentlest current imaginable. And anywhere there's a stronger force holding things together, that force just wins, easily, and refuses to let the new pixel stay. Think of standing on a treadmill belt that's sliding slowly backward under your feet. The belt is trying to carry you away. But you're a healthy person, and the belt is set to a crawl, so you just take a slow step forward now and then, and you stay exactly where you are. The expansion is that belt. The atoms in your arm are bound to each other by the electromagnetic force, which on these scales is monstrously, overwhelmingly stronger. So when space tries to wedge a new pixel between two of your atoms, the bond between them just barks absolutely not and squeezes the new pixel right back out. Same with the Earth and the Sun. Gravity holds them on their leash, no contest. Same with our whole galaxy. Same with the Andromeda Galaxy, which, remember, isn't fleeing us at all. It's the one Slifer caught coming toward us, charging in at 110 kilometers a second. Gravity's grip across the local group is so much stronger than the expansion that Andromeda and the Milky Way are on a collision course. Although, and I love this because it's the universe keeping us humble, a 2025 reanalysis of the data using the Gaia spacecraft by Til Sawala and his colleagues looked again at that collision. It took what astronomers in 2012 had called a certain head-on smash in a few billion years and softened it to roughly a coin flip over the next 10 billion. Even the Great Collision turns out to be a maybe. So the expansion only gets to win out in the truly empty places, the vast, lonely gulfs between galaxy clusters where nothing is holding on to anything. Out there, with no force to veto it, the new space just keeps quietly appearing. The divorce is real, but it only happens in the rooms where nobody's holding hands. There is, though, one thing in the universe that the expansion does get to torture, even though it's screaming across the cosmos at the fastest speed there is: light. Picture a single particle of light, a photon, leaving a galaxy 10 billion light years away, setting out toward us. When it departs, it's young and energetic, a tight, short, blue wave packed with energy. And then it begins, the longest commute in existence. And the whole way here, the universe is doing its quiet trick beneath it, minting new space, lengthening the road under the photon's feet while it runs. The path it's traveling literally gets longer mid-journey. And because the wave is riding on that stretching space, the wave stretches too. The tight little blue wave gets pulled longer and longer. Blue sags to red sags to infrared, infrared sags all the way down to faint microwaves. So that by the time it finally arrives in your eye, after billions of years, it staggers in like a wheezing, red-faced old man, gasping that the road was so much longer than the map promised. That's redshift, the real cosmic kind. Not the galaxy moving away and Doppler shifting like the ambulance, but the wave itself being stretched by the swelling of space it rode across. And it hides a fact so quietly outrageous that it makes physics teachers wince. Blue light carries more energy than red light. So when that wave stretches from blue down to microwave, it loses energy. A lot of it. And here's the question that should stop you. Where did that energy go? And the unsettling honest answer is nowhere. It isn't stashed somewhere. It isn't hiding in the space. In an expanding universe, the neat rule you were taught in school, that energy is always conserved, simply doesn't apply the way it does in your kitchen. I want to be careful here, because it's tempting to say the universe robbed the photon, and that's too dramatic. It's subtler than theft. It's that the law that guarantees energy bookkeeping locally just doesn't have a global version when the whole stage is stretching. The energy isn't stolen. It's that the ledger it would have been written in doesn't exist. And right here, a careful skeptic deserves a hearing, because there's an old, clever objection sitting under everything I've just told you. How do you actually know the light got stretched by space growing? Maybe the light just got tired. That was a real serious idea, proposed by the astronomer Fritz Zwicky back in 1929, the same year Hubble published his law. Zwicky said, maybe photons simply leak a little energy on the long trip, sagging from blue toward red as they go, with no expansion required at all. It's a lovely, economical thought. And it is dead. Because a tired photon and a stretched space photon make one different prediction you can actually check. If space is genuinely stretching, then it stretches everything about a distant event, including its clock. And we can test that because some exploding stars, the type 1a supernovae, flare up and fade on a known schedule. In 1996, watching one called SN 1995K, astronomers led by Bruno Liebengut clocked it fading in slow motion. Its whole light curve stretched out by exactly the amount the expansion predicted. We literally watched a star explode in slow motion because the swelling of space had dilated its clock. Then, in 2001, Gerson Goldhaber and his colleagues did it for 42 supernovae at once and ruled out the no-stretching, tired light prediction by more than 11 standard deviations, which in plain terms means not a chance. A separate test, dreamed up by Richard Tolman all the way back in 1930 and finally carried out by Lubin and Sandage in 2001, checks how the brightness of galaxies dims with distance. And it agrees. Space is really, truly stretching. The photon didn't get tired. The road got longer. We checked. Although, and I'd be cheating you if I tidied this away, we know that space is stretching far better than we know how fast. There's a single number for the rate, and we can measure it two completely different ways, and the two ways flatly refuse to agree. Read it off the oldest light, the baby photo of the universe, the way the Planck satellite did, and you get one answer, about 67. Climb up the cosmic distance ladder instead, rung by rung, out to the nearest pulsing stars whose true brightness we know, the Cepheids, the way Adam Rees and his SHOES team did, and you get a stubbornly different answer, about 73. Those error bars do not overlap. The gap is more than 5 standard deviations wide, which is physics speak for This is not an accident. People hoped for years that one method had a hidden flaw, that the Cepheids were crowded too close together to read cleanly. But in 2024, the James Webb Telescope went and checked and ruled that excuse out to 8 standard deviations. So a full century after Hubble first wrote down a wildly wrong number for this very quantity, we are still arguing with this one number. And nobody, as of now, can make the two answers shake hands. It might mean one team has a subtle gremlin in their instrument. Or it might mean there's a piece of the universe missing from our equations. We genuinely do not know yet, and I find that more thrilling than frightening. All right, we've got a universe made of stretchable toffee, growing by minting new ruler everywhere, fast enough to outrun light in the empty places. Which forces the next box, the one your border cells have been screaming about this whole time. How big is this thing? Does it have an edge? Where does the toffee stop? And to answer that, I need to ask the hardest piece of mental gymnastics in the whole episode. I need you to become an ant. Specifically, a perfectly flat, two-dimensional ant. An ant with no concept whatsoever of up or down, who knows only forward, back, left, and right, living on the surface of an enormous globe. That surface is the ant's entire universe. Now, send the ant walking in a straight line to find the edge of the world. It walks. And it walks. For its whole life, for generations of ants, in one dead straight line, and it never hits a wall. No cliff. No fence. No "you have reached the edge of reality, please turn around" sign. There is no edge, anywhere, in any direction. And yet the surface of that globe is finite. It has a definite, limited area. You could measure it. The ant could, in principle, walk the whole thing and end up exactly back where it started, having never once turned. That's the trick the universe may be playing, and it has a name. Finite but unbounded. A finite amount of space with no boundary anywhere in it. And notice what happens if you ask the ant our question. Ask the flat ant, what's outside the globe? What's the globe sitting inside of? And the ant has no idea what you're talking about. Outside? Up? Those words point in a direction the ant cannot even conceive of, a direction that isn't part of its world at all. To the ant, what's outside the surface isn't a hard question. It's a meaningless one, a typo. And our three-dimensional space might be exactly that, the higher dimensional version of the ant's surface. Finite, maybe. Edgeless, certainly. And the word outside might be for us precisely as meaningless as it is for the ant, a direction we are built unable to point in. But, you say, a globe is curved and round, and frankly, a bit old-fashioned. What if the universe is flat? Good. Even better. Because space can be flat and still have no edge, and the way it does that is a video game. You've played it, or one like it. The little figure walks off the right side of the screen and reappears on the left. Walks off the top, comes back at the bottom. The screen is flat. It's finite. And it has no edge at all, because the edges are secretly stitched together. Right is glued to left, top is glued to bottom. Mathematicians call that shape a torus, a donut, and they probably named it that because they were hungry. And a universe could be built that way, flat, finite, wrapping around onto itself in every direction. And if it were, there'd be a consequence that is either the funniest or the loneliest thing in this entire episode, depending on your mood. Take a perfect telescope and point it dead ahead and look as far as you possibly can. In a wraparound universe, the light leaving the back of your own head could travel all the way around the cosmos and come back to the front. So that the farthest thing your telescope shows you, out at the very limit of sight, is the back of your own head. Every direction you looked, you'd see yourself, repeated, smaller and smaller into the distance. A cosmos-sized hall of mirrors with no door. Wave your hand now, and an unimaginable span of years later, you'd feel a tap on your own shoulder, your own wave, having jogged all the way around everything, come home to find you. And now I have to show you the cruelest little twist in the whole tour, and it's about us, not the ant. Go back to our flat, two-dimensional ant, walking its endless globe.
Its world is expanding. The globe is inflating. And it panics. And it cries out, "But which way?"
Which direction is my whole world expanding into? And we three-dimensional humans, looking down, we'd chuckle, wouldn't we? A little fondly. Oh, you sweet flat thing. It's expanding into the third dimension, into up, the direction you can't see. The answer's obvious. It's just obvious from up here, where we're standing, one dimension above you. Now, feel the floor tilt. Because when we stand at our window and cry out, "What is our universe expanding into?" Is there something standing one dimension above us, looking down, chuckling fondly? A four-dimensional being for whom our entire cosmos is just a soap bubble swelling in the corner of its garden. Who can see straight through our skin to the lunch sitting in our stomach, the way you can see the whole inside of a drawn circle at a glance? A being watching us hunt and hunt for an outside and thinking, look at the little three-dimensional things, still trying to find the edge. I'm not telling you that being exists. I have no idea. But the question, what's it expanding into, might be exactly the ant's mistake, made by us, one floor up. The craving for an outside might just be the blind spot of a creature stuck in too few dimensions to see the answer. Now, scientists are not, as a rule, people who enjoy sitting around feeling vertiginous. They like to go and measure things. And there's a way to test this. If we lived in a wraparound donut universe, there'd be a fingerprint. Light could loop around and we'd see the same patch of distant sky twice, like a repeated pattern in wallpaper. A hotspot here and its identical twin directly opposite, where the same light came around both ways. So they took the most detailed map ever made of the oldest light in the universe from the Planck satellite, and they hunted for those repeats. For the seams of the donut, they found none. And worse, or more wondrously, they found that space is flat, not approximately flat. Flat to an almost insulting precision. Here's what that means concretely. Draw an enormous triangle with its three corners on three different galaxy clusters, billions of light years apart, and measure its angles. In a curved universe, those angles would add up to more than 180 degrees, or less. In our universe, as best the Planck measurements can tell, Planck's number for the curvature is 1/10 of 1%, give or take 2/10, which is science speak for flat as a board. They add up to 180 degrees on the nose. The geometry you learned in school, Euclid's geometry, holds true across spans of tens of billions of light years. In a cosmos full of explosions and black holes and chaos, the large-scale shape of space is laser-cut, mirror-flat glass. And that flatness, with no donut seams to wrap it up, leaves us standing at the edge of the scariest, simplest possibility there is. Because if space is flat and it doesn't loop back on itself, then it just goes on and on and on, forever. A flat, edgeless, infinite universe. Now, I have to be honest with you the way I promised, because here is exactly the spot where it's tempting to oversell. Flat, therefore infinite, is the leading reading, but it is not nailed shut. The flatness we measure is measured only across the patch we can see and only to within those error bars. It's entirely possible the universe is merely so unthinkably vast, far, far bigger than the part we can observe, that our little corner of it just looks perfectly flat, the way a tiny patch of an enormous sphere looks flat to an ant standing on it. We might be blind men with our hands on the thigh of an elephant, declaring the whole beast to be a wall. So, flat as far as we can measure. Possibly infinite. Honestly, we don't know. But all the evidence we have points at the unsettling door. And if you walk through it, that, my friend, is where the real nightmare begins. Because the very first thing infinity does is break your brain with a logic problem. If the universe is already infinite, already endless, then how can it possibly get bigger? What's bigger than infinite? You add one galaxy's worth of new space to something endless, and it's still endless. Infinity plus 1 is infinity. So is the expansion just doing nothing? Is an infinite universe expanding even a sentence that means anything? It is, and to see why, let me check you into the strangest hotel ever imagined, a thought experiment the mathematician David Hilbert dreamed up. Picture a hotel with infinitely many rooms, numbered 1, 2, 3, on forever. And right now, it's full. Every single one of its infinite rooms has a guest. Now a tired traveler walks in and asks for a room. Sorry, you'd say, we're full. But the manager smiles. He gets on the intercom and asks every guest to move down one room. The guest in room 1 shifts to room 2 to room 3, everyone to the room next door. And now, room 1 is empty, and the traveler checks in. The hotel was completely full, and it still found room, without anyone leaving, just by everyone shuffling along. That's what infinity is. It isn't a number, it's a state, and it plays by none of the rules your number instincts demand. An infinite universe can absolutely keep growing, the same way the full hotel always has one more room. The expansion isn't conquering new territory from some outside. There is no outside. It's more like a deepening, an enriching from within. Picture one of those Romanesco cauliflowers, the lime green ones where every little floret is a tiny copy of the whole head, spiraling down into itself forever. A shape that doesn't get bigger by grabbing more table, but by growing more detail, more structure, more itself on the inside. The universe expands the way infinity grows, the hotel, and the way the cauliflower deepens its spiral, not by invading anything, but by becoming endlessly, intricately more of what it already is. Growth without an outside isn't a paradox. It was only ever a failure of small-minded arithmetic. Now we have to deal with the elephant that's been standing in the room since the very beginning, the objection you've maybe been politely sitting on for half an hour. Earlier, I told you that galaxies far enough away are receding from us faster than light, and every fiber of you that paid attention in school is yelling, "That's illegal." Nothing can go faster than light. Einstein said so. You broke the law. I didn't. And the reason is a beautiful loophole, a kind of jurisdictional technicality. Einstein's law, the cosmic speed limit, governs how fast an object can move through space. It's a speed limit on the cars. Nobody, Einstein included, ever put a speed limit on the road itself. Picture Usain Bolt, the fastest man alive, running flat out on a treadmill. His top speed is about 40 kilometers an hour. That's his limit, and he never breaks it. But now imagine the treadmill belt is being cranked backward at 100 kilometers an hour. To you, watching from the side of the room, Bolt, sprinting forward as hard as a human can, is actually flying backward at 60 kilometers an hour. He's receding from you faster than he can run, and he never once broke his own speed limit because he isn't the thing moving fast. The belt is. That's the distant galaxies, exactly. They are barely moving through space at all. They're sitting nearly still on their own patch of dough, their own pixel address, like Bolt running in place. It's the space between us and them. The road, the belt, that's lengthening. And the road is under no speed limit whatsoever. So a galaxy can recede from us faster than light without anything anywhere actually traveling faster than light. And this isn't hand-waving, it's measured. The astronomers Tamara Davis and Charles Lineweaver showed in 2004 that in the standard model of our universe, every galaxy beyond a certain modest distance, past a redshift of about 1.46, is receding faster than light right now, and we have observed hundreds of them. They're not science fiction. They're in the catalogs. The speed limit binds the cars. Nobody ever regulated the road crew. But, and the universe always seems to have a but, that loophole comes with a price. And the price is the cruelest thing in physics. The death of information. Here's the trouble. Once a galaxy is receding from us faster than light, its light can never reach us again. It's not that the light is slow, it's that the road between us is lengthening faster than the light can run up it. Like a child trying to run the wrong way up a down escalator that's moving faster than she can climb. She runs and only loses ground. The light from those galaxies sets out toward us and just never arrives. It falls behind forever. Those galaxies are still out there, still real, still burning, but they have fallen permanently over a horizon. They are physically present and informationally gone, forever. Which means we are holding a single small candle in the middle of an infinite pitch-black forest. The circle of trees the candlelight reaches, that's all we will ever get to see. We call it the observable universe. Beyond that ring, there are more trees, endless more, but their light simply cannot cross the gap to us. And that ring is mind-bending in its own right. It's about 93 billion light years across, even though the universe is only 13.8 billion years old. How can we see something 46 billion light years away if its light only had 13.8 billion years to travel? Because, and this is Davis and Lineweaver again, while that light was crawling toward us all those billions of years, the space it had already crossed kept stretching out behind it, shoving the source ever farther away. The light is like a letter that took 13.8 billion years to arrive, mailed by a sender who never stopped walking away while it was in transit, so that by the time you finally read it, they're 46 billion light years gone. The mail never beats the light, but the road keeps growing under it. And looking out into that ring does something even stranger than show you distance. It shows you time. Because light takes time to travel, every time you look at something far away, you're seeing it not as it is, but as it was when its light set out. Look at this hand in front of your face. Light bounces off it and into your eye in about a billionth of a second, so even your own hand you see slightly in the past. Look at the moon. You see it as it was a second and a quarter ago. The sun, 8 minutes ago. The nearest galaxies, millions of years ago. And the very farthest thing you can see, the wall at the edge of the candlelight, is the universe as it was just 380,000 years after the Big Bang, when it first cooled enough to turn transparent. That ancient glow is still arriving from every direction, the oldest light there is, and we have a name for it, the cosmic microwave background. The wall of the world isn't a wall at all. It's a baby photo of the universe, 380,000 years old, replaying on every patch of sky, forever. The farthest galaxy we've actually pinned down inside that ring is one called MOM-Z14, confirmed in 2026, whose light left it when the universe was a mere 280 million years old. But the microwave glow behind it is older than every galaxy that ever formed. And here is the part that genuinely keeps me up, the affective bottom of this whole stretch, the dread I warned you about. Because the expansion is accelerating, we'll get to why in a moment, galaxies are crossing over that horizon and winking out of our sight all the time. The observable universe is slowly emptying, which means there will come a day, unimaginably far in the future, when astronomers on some world look out and the sky is nearly bare. Every other galaxy will have fled past the horizon. They'll see their own galaxy, and beyond it, black. And so they will reasonably, rigorously, wrongly conclude that their single galaxy is the whole of the universe, fixed and eternal, with no expansion and no Big Bang at all, because every shred of evidence will have slipped beyond their reach. The cosmologists Lawrence Krauss and Robert Scherer worked this out in 2007, and it is a genuinely haunting thought that the truth about the cosmos has an expiration date. We will hold on to it for a little while, and then it will become physically unknowable. We happen to live in the brief window when the fire is still burning low enough to read by, when you can still just barely see the embers of the Big Bang. Far enough downstream, no one will be able to. Hold on to that thought, because near the end, I'm gonna hand it back to you turned completely inside out. And now, deep breath, because this is the one that'll make you wonder if I've come loose. Let me push infinite all the way to its breaking point. If the universe really is infinite, and remember, that's an if, a door we measured open but never walked all the way through, then something follows that sounds like fantasy, but is just cold arithmetic. The number of ways you can possibly arrange the atoms in a region the size of, say, a human being and their room, it's an unthinkably, astronomically huge number. But it is finite. There are only so many distinct ways to stack the same Lego bricks. And in a truly infinite universe, with matter scattered roughly evenly everywhere, every arrangement that can happen must happen, not just once, but infinitely many times. For the same reason that if you flip a coin forever, every possible run of heads and tails eventually shows up. Which means, somewhere out there, unthinkably far away, the exact arrangement of atoms that makes up you and your chair and your room must recur. There is another you, sitting in another identical chair. The physicist Max Tegmark actually ran the numbers on how far you'd have to travel to reach your nearest perfect copy, and got a distance so vast it has to be written as 10 to the 10 to the 29th meters. A number with more zeros than there are atoms in everything we can see. Go a bit nearer and you'd find almost yous, a you identical in every way, except that this morning they had something else for breakfast. A little farther, a you who, years ago, didn't lose touch with someone they loved. I have to be very firm about the hedge here because it would be so easy to cheat you. This is not established fact. It is strictly conditional. It is true only if the universe is genuinely infinite, and the same Planck data that says space is flat says nothing whatsoever about it being infinite. So nobody's going looking for their twin just yet. But if those ifs hold, then it isn't the flaky parallel worlds idea from the movies, where every choice spawns a ghost reality. It's the same physical space as you, the same kind of protons and neutrons, just unthinkably far down the same endless road. Is that comforting? Or is it skin-crawling? Honestly, I feel both at once, and I've never been able to decide. Now, snap out of the philosophy, because there's a gigantic, concrete, physical problem we've been ignoring this whole time, and in 1998, it detonated under the feet of everyone in the field. Here's the problem. The universe is full of matter, galaxies, dark matter, all of it, and matter has gravity, and gravity pulls. So all that gravity should be acting like a brake on the expansion, slowly hauling everything back, the way a stone you throw straight up keeps rising but steadily slows down. For most of the 20th century, every cosmologist agreed the only real question was how fast the expansion was slowing. Whether there was enough matter to eventually stop it and yank everything back together, or whether it would just coast and decelerate forever. So two rival teams set out in the 1990s to measure the slowing. One was the Supernova Cosmology project, led by Saul Perlmutter at the Lawrence Berkeley Lab. The other was the High Z Supernova Search Team, with Brian Schmidt and a young astronomer named Adam Rees. Both teams used the same brilliant trick, a particular kind of exploding star, a Type 1a supernova, which always detonates at very nearly the same true brightness, a standard candle, like a 100-watt bulb. If you know how bright it really is, then how dim it looks tells you exactly how far away it is. And the redshift tells you how much the universe has expanded since the light left. Measure enough distant supernovae, and you can clock the expansion slowdown directly. And in the fall of 1997, Adam Rees ran his data, expecting, like everyone, to see the expansion gently breaking. And the numbers came back insane. To fit them, the universe needed negative mass, a physical impossibility. His own notebook from that moment has the words "shocked me" scrawled right there in the margin. The distant supernovae were coming in too dim, which meant too far, which meant that over the history of the cosmos, the expansion hadn't been slowing down at all. It had been speeding up. His first thought, by his own account, was that he'd wrecked everything, botched the analysis, blown the funding, embarrassed himself, and possibly the whole of physics. He spent weeks hunting for the mistake. Over on the other team, Perlmutter's group was just as sure they'd crossed a wire somewhere. Their team leader, Brian Schmidt, later told the New York Times that his own reaction was somewhere between amazement and horror. Horror specifically at knowing the result was so outrageous that most astronomers would refuse to believe it. Rees finalized the paper, by the way, on the eve of his own honeymoon, firing off replies to a skeptical colleague under what he described as the understandably icy stares of his new wife. Insisting, approach these results not with your heart or your head, but with your eyes. We are observers, after all. And then the two rival teams who'd been racing each other compared notes. And it wasn't a mistake. Both teams. Same answer. The expansion of the universe is accelerating. It was the biggest upheaval in our picture of the cosmos since Newton watched the apple fall. The universe isn't coasting to a stop. It's flooring the gas. So what's pushing? What steps on the gas? Physicists, with their usual genius for naming things, the same poets who gave us the Big Bang and black holes, surveyed this mysterious cosmos accelerating force and called it, with zero creativity whatsoever, dark energy. And dark energy behaves nothing like a normal push. It doesn't shove galaxies apart like magnets repelling. It does something far stranger. It stretches the floor underneath them. It's a property of space itself, causing space to expand faster and faster. The best current guess for what it actually is, and I want to flag that it really is only a guess, the leading hypothesis and not a settled fact, is that it's the energy of empty space. Because here's a genuinely strange truth. Empty space isn't empty. Even a perfect vacuum, scrubbed of every particle, quietly simmers with energy, with pairs of particles flickering into being and vanishing again, a kind of permanent low boil. And that simmering vacuum energy might be the dark energy doing the pushing, which, and this is the irony that makes the whole field wince, would mean that the very thing Einstein once bolted into his equations to hold the universe still was real all along. The term he supposedly later ripped out as the biggest blunder of his life. Deleting it was the blunder. But here is the property of dark energy that should genuinely unsettle you, the one that decides how everything ends. Ordinary stuff thins out as space grows. Spread the same matter over more room, and it gets more dilute. Dark energy doesn't. It comes as a fixed dose per cubic meter of space. It's like space's built-in rent. Every new cubic meter that gets minted arrives with its own fresh, full charge of dark energy attached. So as the universe makes more space, it makes more dark energy, which pushes harder, which makes more space faster, which makes more dark energy still. It's a feedback loop that feeds itself, like coasting downhill on a bike that floors its own throttle a little more with every meter. More space, more push, more space, more push, faster and faster with nothing to ever slow it down. And now, before we hand out any medals, I have to show you the theorists' faces. Because right here is the most embarrassing moment in the history of physics, and it's the channel's honest hedging heart, so I'm not going to skip it. If dark energy really is the energy of empty space, then we ought to be able to calculate how much there should be using our best theory of the very small, quantum field theory. So physicists did the calculation, and the number they got was wrong. Not a little bit wrong. Wrong by, depending on exactly how you do the sum, something like a 1 followed by 120 zeros. The predicted energy of empty space is, by some accountings, 10 to the 120 times bigger than the amount we actually measure pushing the universe apart. It has been called, with no real competition, the worst theoretical prediction in the entire history of science. Let me cash that absurdity out at the grocery store. Imagine you put a single cabbage on the checkout belt, and the cashier rings it up, and the price on the till is the number of atoms in the entire visible universe. That's the size of the gap between what our finest theory predicts and what reality actually does. If the theory were right, the vacuum energy sitting in the volume of your coffee cup would outweigh every star and galaxy and black hole in the sky combined, and would have crushed the cosmos down to a pinhead before anything could ever live in it. The vacuum energy in a single one of your nostrils should, on paper, have ended the universe. And yet, here's the cabbage you somehow paid for and walked away from. You're still standing in the parking lot, alive, which can only mean one thing. We are getting something fundamental about reality badly, hilariously wrong. We do not actually understand the empty space we're swimming in. And honestly, when a door is wedged that far open, you start to wonder what might be on the other side of it. Which brings us at last to the question that's been pacing at the back of this whole hour, the one your border cells never stopped whispering. Is there really no outside at all? Truly? Nothing? And here I want to do something kind, because I've been hammering no outside at you for an hour, and I know it grates. Physicists find it grating too. So they've left you a back door. Several, actually. I have to label every one of them clearly, because we are now stepping off the solid ground of measured fact and out onto the thin ice of frontier speculation. None of this is established. None of it has evidence yet, and I'll keep saying so. But the back doors are real ideas, taken seriously by serious people, and they're beautiful. The first one starts with a question about the Big Bang. What lit the fuse? The leading idea is something called inflation, proposed by Alan Guth, who worked it out on a single electric night in 1979 and wrote across the top of his notebook page, in a double-boxed border, the words "spectacular realization." Inflation says that in the first sliver of a second, the infant universe ballooned by an almost incomprehensible factor, and then settled down into the steady expansion we see today. It's unconfirmed, the leading hypothesis, not a proven fact, but it explains a lot. And then Andre Linde, and separately Alexander Vilenkin, in the early 1980s noticed something wild buried in the math. Once inflation starts, it may never fully stop. It keeps going in the spaces between, forever, like a pot that never comes off the boil. And every so often, a little patch settles down and stops inflating and becomes a universe. A bubble. Our entire cosmos. Everything we've talked about all night, all 93 billion light years of it, would be just one bubble in an endlessly foaming bath. Where inflation happened to stop and let matter and galaxies and us condense out. And the bath is still boiling. Still budding off other bubbles, other universes, forever, possibly with completely different rules inside them. A bubble where light dawdles along at 10 meters a second and everyone moves like they're underwater. A bubble where gravity pushes instead of pulls, and the whole thing blows itself apart the instant it's born. So yes, in this picture, there finally is an outside. But notice it's not the schoolroom warehouse the balloon promised. It's not empty room our universe is expanding into. It's other universes, other bubbles, a whole frothing multiverse. The outside isn't a place we grow into. It's neighbors. Is there a shred of evidence for any of this? Almost none, and I'll say it plainly. But there's one tantalizing, much disputed maybe. Out in that baby photo of the universe, the cosmic microwave background, there's a particular patch. Astronomers found it in 2005 and call it the cold spot. That's a touch colder and a fair bit bigger than the statistics say it really ought to be. About 10 degrees of sky across, the width of 20 full moons lined up. And one physicist, Laura Mersini Houghton, suggested in 2007 that it might be a bruise, a mark left on our universe where our bubble, long ago, gently bumped into a neighboring one. A kiss from another cosmos. I would love that to be true. It is almost certainly not. I have to be straight with you. Mainstream cosmology does not accept this reading. A 2017 survey out of Durham went looking and found that ordinary foreground structure explains only a small slice of the cold spot. And the leading view now is that it's most likely just a statistical fluke, the kind of mild oddity you expect to find somewhere if you stare at a big enough sky. So file the cosmic kiss mark under wonderful if real, probably nothing. But isn't it something that the question is even askable? There's a second back door, drier than the first. If the bubble bath felt a little too wet for you, here's a drier slice of the same idea. And it's, fittingly, bread again. Toast this time. This one is called brain theory, or M theory, and it goes like this. What if our entire three-dimensional universe, all of space, is actually a thin membrane, a sheet, floating in some higher dimensional space we can't perceive, which physicists rather grandly call the bulk? Picture an ant, convinced it lives in a flat two-dimensional world, when really it's standing on a slice of toast floating in a big, airy kitchen. The toast is our universe. The kitchen, the bulk, is the extra dimensions all around it. We'd be a kind of shadow puppet show, the real action happening just off our screen, behind a curtain we can't get around. And in some versions, the Big Bang itself wasn't a beginning at all. It was the collision of two of these membranes, drifting in the bulk and slapping together. Possibly over and over, a cosmic heartbeat of a universe is born and dying and born again. The physicists Paul Steinhardt and Neil Turok worked out a serious version of this, and the lovely twist is that Steinhardt was one of the original pioneers of inflation, who now argues against his own creation. And why would anyone take this seriously? Because it might solve a real nagging puzzle. Why is gravity so absurdly weak? You don't feel how weak gravity is, so let me show you. A tiny fridge magnet, the size of your fingernail, can pluck a paperclip up off a table, which means that one tiny magnet is, in that instant, out-muscling the gravity of the entire planet Earth, all 6,000 billion tons of it, pulling the other way. That's how feeble gravity is next to the other forces. Not a little weaker, but laughably, hopelessly weaker. It's pathetic. And the brain idea offers an answer. Maybe gravity is weak here because it doesn't stay on our membrane. Maybe it leaks off our slice of toast and out into the bulk, like the sound of a loudspeaker bleeding through the wall into the next apartment, so we only feel the faint, muffled remainder. And here's the kicker that ties it back to everything. If gravity can leak out of our universe, could a neighboring membrane's gravity leak in? Some physicists have wondered, very speculatively, whether the mysterious dark matter we can feel tugging on our galaxies but can never see might be exactly that. The gravity of a parallel universe's ordinary matter, an invisible neighbor whose pull reaches across the bulk and into our sky. Every unexplained tug in the dark, a rumor of another world. It's unproven. It's gorgeous. I make no promises. All these universes pile up into one last question, and it's the oldest, most human one of all. With all these bubbles, all these possible sets of rules, why is ours the one that works? Why did our universe come out so improbably perfect for existing? Gravity strong enough to build stars, but not so strong it crushed everything. Atoms stable enough to make chemistry, to make planets, to make us. In a single universe, that fine-tuning looks like a flat-out miracle or a deliberate gift. But in a multiverse, it's just survivor's luck. Think of a lottery. One person winning the jackpot looks miraculous until you remember 100 million tickets were sold and somebody had to win. With countless bubbles, each rolling its own random set of physical laws, the overwhelming majority would come out sterile, too hot, too cold, blown apart at birth. No stars, no chemistry, nothing. Dead. And we find ourselves in a rare, life-friendly one for the most boring reason imaginable. We couldn't have found ourselves anywhere else. There's nobody standing in the broken bubbles to notice they're broken. This idea is called the anthropic principle. Brandon Carter gave it that name at a conference in 1973. And I'll be honest, plenty of physicists hate it because it can feel like an explanation that explains nothing, a way of shrugging at a miracle. But it has a strange feather in its cap. Back in 1987, Steven Weinberg actually used this multiverse reasoning to predict that the cosmological constant, that dark energy number, had to be tiny, but not zero. And when the 1998 measurement finally came in, it landed remarkably close to his prediction. Make of that what you will. The universe may be fine-tuned for you, not because you were planned, but because you're standing in the one room where standing was possible. We have come a very long way, you and I. We popped the schoolroom balloon. We baked Hubble's raisin bread and learned that the dough, not the raisins, does the running. We tumbled through Einstein's Toffee and upgraded the resolution of space pixel by pixel. We were a flat ant hunting for an edge that wasn't there. Got trapped in the donut and saw the back of our own head. Counted the rooms of an infinite hotel and met an impossible copy of ourselves out at the end of the road. And somewhere in there, admit it, the floor tilted under you at least once. We watched the universe get caught speeding in 1998, found out empty space charges rent, and that we're wrong about the rent by a number with 120 zeros in it, and finally pressed an ear to the neighbor's door. If your brain feels, right about now, like cheese that's been left in the microwave too long, I promise you, so does mine. But there's one question we set down at the start and never picked back up, and we can't leave without it. How does it all end? Start with the loudest way it could go, the one that follows if dark energy turns out to be even stranger and stronger than we think, the so-called phantom kind. Physicists call it the Big Rip. If that's how it goes, the runaway acceleration doesn't just push the galaxies apart, it eventually gets inside everything and tears it. Caldwell, Kamiankowski, and Weinberg laid out the cascade in 2003, and it reads like a doomsday kitchen timer counting down the final billions of years. First, the galaxy clusters get stripped apart. Then, with about 60 million years left, our own Milky Way is unbound. Then, with around 3 months on the clock, the solar system comes apart. The Earth pulled away from the Sun. With half an hour left, the Earth itself is torn open. And in the last unimaginable sliver, 10 to the minus 19 of a second, the very atoms are ripped to pieces. And then, space and time themselves shred. I have to hand you the hedge, though, and it's a real comfort. This is conditional. It only happens if dark energy is that phantom kind, and the best measurement we have, from Planck, says dark energy looks like the plain, steady sort, consistent with no rip at all. The Big Rip is a vivid maybe, not a forecast. You can let go of it. Swing to the opposite extreme then, and you get the Big Crunch, the mirror image, where one day the expansion reverses, gravity wins after all, and the whole universe falls back together into a single point. It's the tidiest, most cyclical story. It's also, right now, the least likely of the lot. A flat universe that keeps expanding doesn't naturally recollapse, and Planck says ours is flat. So set that one mostly aside too. Which leaves the likeliest one, and the quietest. The Big Freeze. The long, slow cold. In this ending, the one our best current understanding actually points toward, nothing tears and nothing collapses. The universe just keeps expanding, gently, forever, getting colder and emptier and more spread out, until it simply runs down. The physicists Fred Adams and Gregory Laughlin mapped this out in 1997, era by era, and the timeline is so vast it stops meaning anything. For a while, for about 100 trillion years, stars keep being born. Then the gas to make new ones runs thin, and the last stars flicker out, one by one, like the last embers of a fire nobody's tending. Then come the long, cold ages of dead remnants, cinders and corpses of stars drifting in the dark. And then, far, far later, by around 10 to the 100 years, a 1 with 100 zeros after it, even the black holes, the last things left, slowly evaporate away into nothing. To give you a sense of that number, if the entire 13.8 billion year history of the universe so far were a single tick of a clock, then the age when the last black hole dies hasn't even begun to tick. And after that, nothing happens. Ever again. A uniform, lifeless cold. The same faint temperature everywhere. No structure, no light worth the name, no events. The Victorians actually saw this coming first. Hermann von Helmholtz and Rudolf Clausius, who coined the word entropy, argued back in the 1850s and 60s that the universe must eventually wind down to a still, workless, uniform warmth. Though I'll keep honest even here, the very last chapters of that timeline lean on the proton eventually decaying, which we have never actually observed it do. So even the cold ending keeps a little mystery. And that's the part that aches, isn't it? Because everything we've ever loved is inside this story. Every symphony, every first kiss, every face you'd know in a crowd. This very hour you're spending listening to me. All of it, eventually, in the long cold, forgotten. Not destroyed in fire, not crushed in a crunch, just slowly, gently, run down into the dark until there's no one and nothing left to remember any of it happened. So let me pour you the last cup of tea in all of this, because I did promise there was something waiting behind the final wall. We have spent this whole hour knocking the walls out of boxes. We threw away the balloon's living room. We deleted the grenade's warehouse. We learned there's no edge to reach, no outside to grow into, no center to stand at. And every one of those felt, didn't it, like a small eviction? Like the universe gently telling you that you are nobody special, adrift in a vast, indifferent nowhere, a tiny bystander pressed up against the glass, peeking in at a cosmos that doesn't know you're there. But go back to the Raisin loaf, and the thing I told you to tuck away and keep safe. Remember what no center actually turned out to mean. It didn't mean there's no center anywhere. It meant that every point is the center, that from every single spot in the entire universe, all of creation appears to be arranged around you, fleeing from you, organized about you as the still point of the turning world. There is no center, which is precisely, mathematically, the same thing as saying the spot where you are standing right now is the center of the universe. Not as a comforting figure of speech. As the literal, only honest answer to where's the middle? And I want to be careful and truthful the way I've tried to be all night. This is meaning, not a special physical permit. The laws don't single you out. Physics says no spot is privileged, and that's exactly why yours is as central as any. But sit with what it gives you. The next time you step outside and look up at all those galaxies, understand that they are not fleeing because they're abandoning you. The expansion of the entire universe, all 13.8 billion years of it, is arranged so that you sit at its focus. Every receding galaxy in the sky, pouring its ancient light inward across billions of years to converge on the back of your one retina this instant. You, exactly as you are. Maybe a little tired. Maybe a little nearsighted. The focal point of all of it. So here is the thing that was waiting behind the last wall, and it's the warmest truth I know. You were never an outsider peeking in. That whole feeling, the bystander at the glass, the lonely corner of nowhere, was just your edge-finding brain, your faithful old lion-spotting organ, looking for a wall one last time, and not finding one. There is no glass. There is no outside to be exiled to. The Big Bang happened here, under your feet, as much as anywhere, and the primordial energy of that first instant didn't fly off and leave you behind. It cooled. It slowed. It gathered itself into dust, and the dust into stars, And the stars forged it into the carbon and oxygen and iron that are right now reading these words and turning them into thought. You are not separate from the universe, watching it expand. You are a piece of the universe that has cooled and condensed and complicated itself just enough to wake up, to grow eyes and turn around and look back at the rest of itself in wonder. The cosmos built an organ to perceive itself, and you are it. When you look up and feel small, that is the universe looking at the universe and feeling small. It expands through you, through every breath, every thought, every flicker of that very curiosity that brought you here to ask what it's all expanding into. And the answer, in the end, was never a place. It was you. Maybe that's the warmest truth we get to hold before the long cold ever arrives. That the universe has no edge, no outside, and no center. And so, somehow, against all of it, the center is exactly where you are. There's the popped balloon in your hand. Turns out it was never the universe at all. You were closer to that all along. Funny old organ, the human brain. Spent a few 100 million years learning to find the one edge that would keep it alive. And the one time it finally goes looking for the edge of everything, the only thing it finds, waiting behind the last wall, is its own face.